we don't really... we don't really need to consider this last equation, right? Because if we know the total population size, and we know S and we know I, then that determines R. So in some sense, this is really a system of two differential equations. Okay, so consistency, we proved that the limits S infinity, R infinity, I infinity exist. I showed you this measles data from the UK in the 10-year period, 1948 to 1958, which was pre-vaccination. Something I didn't point out, which is going to be important later, is look at the period. There's a 2-year period there. And the next model is going to recover that period, as you'll see. But obviously, the limit I infinity, so to speak, is not existing, right? The number of infectives is not going to a limit. So measles in the UK during this period cannot be modeled by an SIR model. Okay, and then I think I ended the last lecture by proving that the disease dies out, that I infinity is equal to 0. Okay? Okay, so this is kind of the great man, Sir Ronald Ross. So he's the father of mathematical modeling of transmission of infectious diseases. He was the first one to write down an SIR type model. It's actually more sophisticated than the SIR model. It's what's these days called the crisscross SI model. He wrote it down for malaria. So you actually had an S and an I for the mosquito and an S and I for the human, and then the mosquito S and the human I, and the mosquito I and the human S interact through mass action. So this is in the notes, which I'm not going to talk about. But that's also a model, the first model for gonorrhea. Okay, so here's our first theorem. So we define the most important quantity in epidemiology, which is R0 or R0. So it's equal to the initial number of susceptibles times beta divided by nu. Okay, in a few minutes we'll discuss biologically what this means, although it's not very hard to figure this out. But this is R0. And the theorem, which essentially is due to Ross, I mean, he was the first one to prove this, again, in a more complicated case, is that if R0 is less than or equal to 1, then the disease quickly dies out. And in fact, if R0 is less than 1, we'll see that it dies out with exponential speed. And if R0 is bigger than 1, then the number of infectives starts increasing. It reaches some maximum, and then it decreases monotonically to 0 as t goes to infinity. So R0 determines whether the disease dies out or whether it starts increasing. Okay, so this is what's called the threshold theorem. Let me just go back to the model and say one more thing, because we'll need it soon. Suppose we're interested in the maximum number of infectives, which we will be soon. So why might you be interested in the maximum number of infectives? Well, if you have to plan for hospitals, for ventilators, and so on, you might be interested in that. So that's going to occur when I dot is equal to 0, so the critical points, of course, are when I is equal to 0, or when S is equal to nu over beta. And you'll see why that's going to be important in a few minutes. Okay, so before I prove the theorem, let me make two important definitions. So the first definition is not well defined in the literature. This is my attempt to make it well defined. So a disease is endemic, just in words, if it doesn't die out. If it's always present in some number in the population. So I'm defining a disease to be endemic if the lim inf as t goes to infinity if the number of infectives is positive. So property 3 says that I infinity is equal to 0. So obviously, for this most basic SIR model, there's no endemic disease. And then an epidemic is said to occur at some time if the number of infectives at that time is increasing. Again, this isn't the best definition, but this is the definition in the literature. So from Theorem 1, remember, Theorem 1 says that if R naught is bigger than 1, the disease starts increasing. So an epidemic occurs at t is equal to 0. And these aren't mutually exclusive because you can have endemic disease that increases, decreases, increases, decreases, increases, decreases, which corresponds to maybe infinitely many epidemics. Just to confuse you a little bit. Okay, so now the proof. And the proof is very simple. So we use the second equation. So I prime is equal to beta s minus nu times I. Now we use the fact that s of t is less than or equal to s of 0 for all t, right? We prove s of t is always decreasing. So we have derivative of I is less than or equal to this constant times I. Integrate that. So I of t is less than or equal to I naught e to the t times this expression. Now use the definition of R naught. So we put in we just rewrite this expression using R naught. So I of t is less than or equal to I0 e to the t times nu times R naught minus 1. So clearly if R naught is less than 1, I of t is bounded by something which is going to 0 with exponential speed. Okay? Okay, so now let's prove the second part. So assume that R naught is bigger than 1. So again, write down that second equation and let's compute things at time 0. So I prime of 0 is equal to, well, beta S0 minus nu times I naught. And again, let's put in our definition of R naught. So I prime of 0 is equal to this. Now clearly, if R naught is bigger than 1, this expression, whatever it is positive, right? Assuming that I of 0 is positive. Right? Because if there are no infectives at time 0, then there are no infectives for all time. So if we assume that the number of infectives is positive, the number of infectives at time 0 is positive, then certainly I prime of 0 is positive for R naught bigger than 1. So that says that the number of infectives starts to increase. Right? So the number of infectives starts to increase, but we know that the number of infectives has a single maximum when S of t is equal to nu over beta. So the number of infectives increases until the number of susceptibles is equal to this number. And then we showed that I of infinity is equal to 0. So the number of infectives increases, right? It has one maximum. Then it decreases for all future time. And it decreases to 0 because I proved to you that I of infinity is equal to 0. Very simple. And if not, I'll leave that as an exercise. Okay, so this is, in some sense, the main theorem. Okay, so here's your first quiz. So there's a red curve, a blue curve, and although it's hard to see a green curve. Which curve corresponds to the number of infected? The blue curve. What curve corresponds to the number of susceptible? The red curve. Okay, so let's go back to the system and let's prove some more things. So the next thing I want to prove is the existence of a second conserved quantity. So what we're going to do is we're going to take this first equation and we're going to divide it by the second equation. So we have ds divided by di is equal to minus beta si divided by beta si minus nu I, and we cancel an I. and this is what you get. You cancel the I, and what you have is a first-order differential equation. ds di is equal to something involving just s. So it's a separable equation. You can rewrite this differential equation like this, with s and ds on the left-hand side, and there are not even any i's because we canceled them, just di on the right-hand side. So you integrate both sides, and you get, well, that's just a very, simple calculus. You get that minus s plus nu over beta log s is equal to, when you integrate the right-hand side, I plus a constant. So just translating that into the right language, that says for every value of t, I of t minus s of t plus nu over beta log s of t is equal to the constant. And what's the constant? Well, the constant is that expression at any time. Let's take it to be time 0. So I claim that this calculation shows that for all time bigger or equal to 0, I of t minus s of t plus nu over beta log s of t is constant. This is a big sign problem. This you get 2 beers or 2 caipirinhas if you can explain to me biologically what this quantity is. Frankly, I don't know. I'll make it 3 caipirinhas. Okay, so it's clear? Okay, so what this does is it lets us write or plot parametrically I of t versus s of t. So if you plot I of t versus s of t, these are the curves you get for different initial conditions. Now we know that, we're starting here, and the curves are sort of, the motion is this way. We know that we proved that I infinity is 0, right? So we know that all these curves have to end on this axis. Now, if you look carefully, you'll notice, if you're observant, that how about s infinity? Is s infinity equal to 0? Well, maybe, maybe not. Not so clear from these plots. And I'll come back to that in a second. So before I come back to that, what is the maximum number of infectives? So as I mentioned before, there are public health reasons why this is very important to know. Can we compute the maximum number of infectives? And the answer is yes, and it's an immediate consequence of that second integral, that second conserved quantity. So we have this expression is true for all time. So in particular, it's true for that time which maximizes the number of infectives. Right? At that time which maximizes the number of infectives, we know that s of t is equal to nu over beta. Right? That just comes from the differential equations. That's it. That's it, because we know that tells us that I max minus s at when I is max, which is nu over beta, plus nu over beta log nu over beta is equal to this stuff, which is just initial conditions and nu over beta. So what we obtain is a very nice formula for the maximum number of infectives, just in terms of I naught, S naught, nu, and beta. So it's a very nice formula. Now, when I lecture on this at Georgia Tech, I usually ask my students to write down 2 questions which we can't answer from this analysis. And one question is, at what time is the maximum number of infectives? At what time does the maximum number of infectives occur? Right, that might be useful. Is it going to occur in 3 weeks? Is it going to occur in 3 months? That you can't get from this type of analysis, but you can get the maximum number. Okay? Okay. So now, how did epidemics end? It was believed for a long time that they ended because there were no more susceptibles in the population. Essentially, everyone got sick. Now, it might sound a little bit silly now, but I think for at least 100 years, people believed this. So if this is true, then S infinity is equal to 0. Right? S infinity is equal to 0 means everybody got sick. So is it true that S infinity is equal to 0? Well, the next theorem is going to show that this is false. So it's not true, at least in this model, that epidemics end because there are no more susceptibles. What this model shows is that epidemics end because of a lack of new infectives. So this is a little bit subtle. It's not deep, but it's a little bit subtle. One needs to think about that a little bit. So the theorem is that S infinity is always positive, and it's always, here's a lower bound, a positive lower bound. So S infinity, whatever it is, it's always bigger or equal to S naught e to the minus beta, the total population size, divided by nu. And clearly that expression is positive. So how do you prove this? Well, again, the proof is very simple. We're going to take the first equation and we're going to divide it by the third equation. Yes?
So it's possible for everybody to be sick?
Yes. Yes. In this model, yes. So so you take the first equation, you divide it by the third equation, you get ds dr is equal to, well, this I cancels with this I, so you just get minus beta over nu times s. That's all we're going to use. So, right. So ds dr is equal to what s is, what r is, so it's minus beta s over nu. And again, this is a separable differential equation, right? You write this as ds divided by minus beta s is equal to, what is it? Nu times r, something like that. It's separable, you integrate, and when you integrate, you get that s of t is equal to s of naught e to the minus beta times r of t times nu. Now, you don't know so much about r of t, but you do know that r of t is always less than or equal to the population size. Right? So s of t is always bigger or equal to s naught e to the minus beta, the population size divided by nu, and that's what I'm claiming. So again, uniform lower bound for s infinity. Okay, so here's, boy, that's a little bit hard to see. I apologize. So S infinity is equal to, remember, I infinity is 0, right? And the total population size, S infinity plus I infinity plus R infinity is n. So I infinity is 0. So that's what I'm using here. S infinity, on one hand, by, if you like, by a little calculation, it's equal to S0 e to the minus beta R infinity over nu. And on the other hand, since I infinity is equal to 0, it's equal to this. So we have S infinity here, and we have S infinity here. So what we have is a transcendental equation for S infinity. Right, so S infinity is a very important quantity because it's the number of people that did not get sick at the end of the outbreak. Right? Okay, so we have a transcendental equation for S infinity. If you're a little bit clever, you'll look at the proportion of individuals which did not get sick. That's x. And then some simple algebra says that log x is equal to r naught times x minus 1. So that's a simpler transcendental equation for the proportion of susceptibles for large time. So now you plot that. So first of all, you see that the proportion of susceptibles at time infinity just depends on R naught. If you know R naught, then you know how many people, what proportion of people are going to get sick. That's very important. That's extremely important. That's one of the reasons why R naught is such an important quantity. It's going to determine the percentage of the population that gets sick. So this is the curve that you get. So this axis is R naught, and it's ranging from 1 to 4.5. And you see that for R naught, maybe 1.5, something like 0.4, 40% of the population doesn't get sick. But for R is equal to, say, R naught is equal to, say, 4, then at the end of the outbreak, this is like 0.1, maybe 90%, only 10% of the population does not get sick. Okay, so we're going to talk a few slides about R naught. So again, this is our definition of R naught. So what is it? It's a product of, well, 1 over nu tells you how long a person is infected per unit time. Kappa times S0 over n tells you the number of contacts that an infected person has with susceptibles per unit time. And tau is the probability of transmission of the infected person making the susceptible sick during a contact. So if you put these all three together, what you get is that R naught is the number of new infections caused by each infective person per unit time. That make sense? This is extremely important interpretation. So again, just think what these three terms mean, and I claim putting it together, you get that R naught is the number of new infections caused by each infection at time 0. Okay? Now, this is usually taken as the definition of R. So this is our definition of R naught in terms of our model, in terms of our SIR model with beta and with nu and so on. And this was our interpretation. But one can define, and if you take any book on epidemiology, they will define R naught this way, that it's the number of secondary infections caused by each primary infection at the beginning of the outbreak. And that has nothing to do with our model. Okay, so let's bring in some data. Okay, so I want to so-called confront our SIR model with data. So what that means is we need to choose beta and nu to somehow achieve a best fit of our SIR model to data. Now, this, many books are written about this. How do you choose beta and nu? Kind of the old-fashioned way of doing it is least squares. But nobody really uses least squares anymore. Many people use maximum likelihood methods. And this is sort of a whole class of methods. And then frequently, you have some information. You know some things. You have some sort of a priori information, which you'd like to kind of use that information. And if you can add that type of information to maximum likelihood using what are called Bayesian methods. So let me give you, I think, 5 examples. So, and in the notes, I talk about why you see these same examples, although I'm going to show you one that most people don't know about. I explain in the notes why you tend to see the same examples over and over and over again. And the point is that it's very hard to obtain new data for infectious diseases. So this is a very famous data set from Bombay plague in 1905, 1906. Here you see weeks from 0 to 30. Here you see essentially the number of infectives. Essentially, everyone that got sick died. And the black dots are the data points, the number of people that died that week in Bombay from the plague. And these guys did actually, it was the least squares fit, and the curve you see is the output of the SIR model with somehow optimal parameters. And the white dots are the values of that output at 1 week, 2 week, 3 weeks, and 4 weeks, so on. Is it a good fit? Let me keep going. This is a more recent example of flu in a boarding school, actually a large boarding school of hundreds of boys during 1978. So this is in days, from day 0 to day 14. And this is the black dots are the number of infected. And again, what they did was, I guess this is Murray, who wrote a famous book on mathematical biology, is he fit an SIR model to this data. And it's this curve. It doesn't look like a bad fit, does it? Okay, here's dengue. This is from, I guess, northern Brazil. This is from, I guess, a city in Cuba. These are outbreaks, oh boy, I forget when. Maybe not so long ago. And again, the blue dots are data points, and the curves are fits of SIR models through the data. Not so bad. Not so bad for dengue. There's a disease called hog for pig, cholera. Otherwise, the technical term is a CSFV, classical swine fever virus. This is kind of a mad cow type disease for pigs. And there was an outbreak in the Netherlands, 1997 to 1998. And again, I apologize. This is a bit hard to see. Can you see the data points? Okay. Those are the data points, and this is somehow the best SIR, the best fitting SIR model to that data. Not bad. Not bad. Let me skip that. Okay, so I showed you, I think, 5 plots. They look pretty good. But you have to be careful. And I talk about this in the book. You have to be very, very, very careful before you believe that these are good fits. And the danger is what I write in red, that the data was used to so-called parameterize the model to find beta and nu. So what you have to worry about is that the model is just regenerating the data that was used to parameterize it. Okay, if you learn anything from these lectures, or if you think about anything in these lectures, think about this, because this applies to much of statistics. So again, you have to be very, very careful, because we use the data to parameterize the model. We use the data to find beta and nu. So the worry is that the model, the output of the model, is just essentially regenerating the data. So what can you do about that? Well, as I say, more convincing would be if we take our model of, say, dengue in, I don't know, Havana, parameterized, and then we apply it to a dengue outbreak in another city. So we use this parameterized model on another data set, a new data set. And if that does a good fit, then you're much more confident that this model is actually describing some reality. Does this make sense? Yes? Okay. So here is another example. Actually, this is Havana 2001. Good fit? Is it a waste of time to have done this? So obviously it's a bad fit. Somehow it looks like there are several pulses, several waves of the outbreak. But I claim that even though obviously an SIR model doesn't fit the data very well, this wasn't a waste of time, because if you look at the three data sets, three time series, the two from before and this one, your eye really can't tell them apart very much. But trying to fit this SIR model, you see that somehow this outbreak is very different than the other two outbreaks. So even though the model is a terrible model, it's giving you some useful information that somehow this outbreak is different. Okay, so again, I discussed this in detail in the book. The old paradigm of mathematical biology is papers are written by mathematicians to be maybe not so nice. Frequently what happened was that a mathematician worked in PDEs or ODEs, had a favorite technique. Somehow they learned about some differential equation that has something to do with biology. They changed it to make it of the form that they study, and then they prove something about existence or uniqueness or something like that. And that was mathematical biology. So it was very rare in old papers in mathematical biology, and old isn't that long ago, to have any data. In fact, probably most mathematicians would have said, why ruin a good paper with data? But times have changed. Times have changed. So now many papers, if you pick up Journal of Mathematical Biology, Bulletin of Mathematical Biology, American Naturalist, even papers in Science and Nature, they're frequently written by mathematicians and biologists. And there are theoretical papers where you just somehow there's no data available. But if it's possible to confront your model with data, it's expected that you do it if you want your paper to appear in a good journal. So I think this is, at least for me, a very healthy change in sort of the culture of mathematical biology certainly in the last 10 years. Okay, so this is also very important. So you're obtaining data, population data, also data for spread of infectious disease, new data, is very, very difficult. There are lots of reasons for it. And again, I describe them in the book. Many researchers don't want to share their data. That's a big problem. The culture is changing, but it seems to be changing slowly. There's confidentiality problems with data, with infection data. There are issues with health departments. They don't care about collecting all the data they can. They care about stopping the outbreak. So once they've controlled the outbreak, many times almost always they'll stop collecting data, because collecting data and then analyzing data is expensive. So there are many reasons why it's very difficult to find good new data for populations or for infectious diseases. So I say that your best chance to obtain useful data is to be working with a biologist, an epidemiologist, a physician, or a biostatistician. Or if you're a mathematician doing a thesis, you work with a thesis supervisor who collaborates with epidemiologists or biostatisticians. Okay. So again, R0 is the number of secondary infections generated from each primary infection at the beginning of the epidemic. And here are some typical values. This is from Anderson and May's book. I forget the title, but this is the Bible of modeling infectious diseases in humans. And the title is something like that. So you see malaria, over 100. Right? It's in a class by itself. Measles, 12 to 18. Pertussis, 12 to 17. Chickenpox, 9. Dengue is 3. SARS, 2 to 5. 1918 pandemic flu 2 to 3, Ebola 1 to 2, H1N1, I hear the latest estimates being about 1.3. Now you'll notice, okay, so here's a quiz. You'll notice that smallpox has an R naught about 3 to 5, and that HIV, AIDS, has R naught about 2 to 5. So they have the same R naught. Does that make sense? So here's the definition of R naught, and let's look at HIV/AIDS. What is one over nu is how long people are infected. Big number or small number? It's a very, very big number, right? People are infected for a long period of time, years. Also, the probability of transmission. Not so large, kind of small, right? Or at least not so large. On the other hand, for smallpox, people are infected, it's a virus, like chickenpox or something. People are infected for 1 week, 2 weeks, and the probability of transmission is pretty high. It's a pretty contagious disease. Okay. Also, different outbreaks of the same disease can have very different R naughts. So there was a 1962 outbreak of measles in Senegal, and it had an R naught of something between 1 and 2. On the other hand, there was an outbreak at roughly the same time, 1955 to 1958 in the US, and that had an R naught of 5 to 6. Does that make sense with this definition of R naught? So what's different between Senegal and New York City? I'm sorry? Population size, yes. But you think, I'm sorry. Right, number of contacts. So kappa, you would think, would be, say, much higher in New York City than it would be in Senegal. Good. Okay. Now, as I'm trying to argue that R naught is extremely important. It's the most important quantity associated to infectious disease, but it's not everything. So in particular, this is kind of interesting. The Spanish flu from 1918 to 19, the Asian flu 1957 to 58, the Hong Kong flu 1968-69, and SARS all had about the same R naught. But if you look, the Spanish flu caused about 500,000 deaths in the United States. The Asian flu caused about 70,000 deaths in the United States. The Hong Kong flu caused about 34,000 deaths in the United States, and SARS caused 800 deaths around the world. With the same R naught. Okay, so one more quiz for today. What time is it? This is Public Health 101, as we say. How do you prevent an epidemic? I'm sorry, I can't.
You must stay in your home.
Well.
Must lower the number of infected or lower the number of contacts?
Yes, but say it in terms of what we've been talking about. Think of theorem 1. How about make R not less than 1? Okay, that's essentially what you said. But if you can make R naught less than 1, then again, if your disease follows this model, you will not have an epidemic. So how do you make R naught less than 1? So this is what I'm about to say is kind of well, it's totally obvious, but it's really the theoretical underpinning for public health policy. It's the framework of which public health policy is built on. So to make R naught less than 1, you can reduce tau, you can reduce kappa, you can reduce S naught, and you can increase nu. Okay? In other words, you can decrease 1 over nu. So 1 over nu is how long a person is infected, how long they're sick. So how can you reduce that? I'm sorry? Drinking? Oh, treating. So maybe drugs. Antibiotics, antivirals, that will speed up their recovery, right? Reduce the amount of time that they're infected. So if you have cholera and you're given an antibiotic like tetracycline pretty quickly, then instead of being sick for 4 days, you'll be sick for 3 days, maybe 3 days minus epsilon, something like that. Okay, how about tau? How do you reduce tau? So that's the probability of transmission during a contact. Say again?
Vaccinating the susceptibles.
Okay, you can vaccinate the susceptibles so that there's less. Fine. How else?
The way of transmission.
So how do you protect? So think masks, right? I mean, during SARS, for instance, you saw lots of people in Toronto and so on walking around with masks. That will certainly, well, almost certainly, decrease tau. For sexually transmitted diseases, you use things like condoms to decrease tau. How about kappa? How do you decrease kappa? Quarantine, isolation. You just tell people stay at home. How about S naught? Vaccine. And although you don't do this to humans, for animals like foot and mouth disease, how do you decrease S naught? You kill them, yes. You don't kill them, you cull them. Okay, so that's what these slides say. How much time do I have? Let me see. Okay, 5 more minutes. Let's talk about vaccination. So vaccinating susceptibles removes them from the susceptible class, right? And puts them really into the removed class. So here's a question. Can an epidemic be prevented? So let me back up. You may or may not know that not everyone can receive a vaccine. So for childhood vaccines, presumably around the world, there's probably 3% of children that are sick, that have cancer or compromised immune systems where they cannot receive many vaccines. So those children, even though you might be vaccinating them against a terrible disease, you do more damage with the vaccine than without the vaccine. So that's 3%. So there's no way you're going to cover 100% of the population. Right? People are always going to refuse vaccines. You're not going to be able to find everybody in the population. So the question is, can an epidemic be prevented by vaccinating only a fraction of the susceptible class? Right? That's the question. And if the answer is yes, then what's the smallest fraction you need? And we can now answer the question very easily. So let rho be the fraction of the susceptibles that get a vaccination. And let's assume that the vaccine is 100% effective. And as I mentioned last lecture, measles vaccine is only about 80% effective. But it's easy to modify this, and it's actually a very good two-line exercise to modify this argument, assuming that the vaccine is only, say, 80% effective. So rho is the fraction of susceptibles that get the vaccine. So R naught is equal to, well, we have a new S naught, right? Because 1 minus rho percent of the S naught are no longer S naught, are no longer susceptible. So the new number of susceptibles is S naught times 1 minus rho. And then we have the same beta and the same nu, and we want that to be less than 1. And then we solve for rho. And what you see is that rho has to be bigger than 1 minus 1 over r. So this little calculation shows that if you vaccinate 1 minus 1 over r naught percent of the population, then you'll prevent an epidemic. You'll have r naught less than 1. So for instance, and this is what's called herd immunity. So again, so this shows something which is not obvious. And this is another great application of mathematical modeling, which you're not going to see any other way. You're not going to see this from data. You really need mathematical modeling to see this, that vaccination can prevent an epidemic without making everyone immune. And if you just put in some sample values, so for smallpox, where R naught is about 5, 1 minus 1 over 5 is about 80%. So to prevent an epidemic, you need to vaccinate 80% of the population. But for malaria, where R naught is bigger than 100, you have to vaccinate almost everybody. Okay, let me stop here for today. Thank you.